Hello everyone, my name is Robert, and this is Lab 1 for Physics 2, Charge Tape. So the purpose of this lab was to investigate the charge on a line of tape necessary for it to float above a similarly charged line of tape. For this, we used an experimental data model, just testing with tape and see what we can measure for the distance, and we also ran some computational models, modeling a point charge as well as a line of charge. At the very end, the computational model gave us an electric force of 4.55 e to the negative 4 newtons, and the gravitational force supposed to be in balance with that was 8.6328 e to the negative 4 newtons. So fundamental principles for this lab, we use the momentum principle, going back to Newton's second law, as we're working in static equilibrium between the force electric and force of gravity. Electric charge, which we know force electric is 1 over 4 pi epsilon naught, charge over distance squared r hat, with the force electric being a charge times the external electric force. And to balance out the electric force, we of course are using gravity near the surface of the Earth, which is Fg in the negative y direction. So for the experiment itself, once we pulled the tape apart, I set one tape on the bottom and floated one above. They are both positively charged. The distance we found between them was 0.03 meters or 3 centimeters. To find the mass of the tape, I actually used more tape, around 24 inches, and then divided that to find my 5 inches of tape, which 5 inches around 0.13 meters, and then dividing that across the total length and its mass, I found that the mass of my 5 inches was 0.000088 kilograms. For this, we had to assume that Earth was the only thing in the surroundings. We're not accounting for air resistance, and there's errors in this as the tape lost excess charge due to increased humidity, as well as measurements was a little bit inaccurate because of the ruler wanted to attract the tape as well, so it was a little bit difficult to get an exact measurement. Using the force of gravity, and setting the force of electric to force of gravity equal to each other since they're in static equilibrium on the top tape, we found that QB, square root of the force of gravity times d squared over Coulomb's constant, estimated the charge to be 9.28 e to the negative 9 coulombs. Still assuming this to be a point charge across the whole tape. To answer the lab questions, we found that the number of electrons lost was 5.8 e to the 10 electrons lost. Dividing the charge of the tape we found by the charge electron. To find the ratio of electrons lost, we took the number of atoms in the area of the tape, which we estimated by the length of an atom, multiplying it by the actual area in length and width. And divided by the number of electrons lost, we found that per 4.16 e to the 6 atoms, there was about 1 electron lost. So looking at the first computational model, we are assuming that the initial conditions we set from the experimental distance is 3 centimeters, mass of the tape as given. Again, we're assuming that the tape is 1 point charge for each, and we're only including the Earth and surrounding, not including any air resistance or other effects. The calculated point charge was the same as the experimental, 9.28 e to the negative 9 coulombs. We can see that I have force electric versus force of gravity on tape B. Looking at the second model, looking at a line of charges, this time we're going to assume a uniform charge distribution against the same mass, and we're going to borrow the Q from our first model, again assuming that the Earth is the only thing in the surroundings. As well, we're going to set a function for E field that's going to find a point charge for our DE points. As we can see, it's 1 over 4 pi epsilon naught times Q over the magnitude of R squared times R hat. So essentially what's happening in the two for loops for this model is that for every point on the top tape, we want to find the external electric force being acted upon it by the bottom tape. So we look at each infinitesimal point for its dq, estimating from E field for each point, using that to find the electric force for each point, and then going across each point as we iterate through, and that gives us our graph, which we can see here. So to wrap up, to answer the first what if they were swapped, we would still see repulsion of similar charges. It would just be caused by different particles or the opposite particles. we can see that from the second model, we found the magnitude of the line charge electric force was 4.55 e to the negative 4. The magnitude of gravity, which should have been equal in theory, was 8.63 e to the negative 4 newtons. So around the same magnitude, but it was about double, which would have caused it to fall, but we see that it was floating. This could have been due to errors such as humidity, imprecise measurements, assumptions of a point charge, but we saw that using a single point charge got us in e to the negative 3 range, which would have been too big, or of course estimating how many point charges are actually affecting the line.